Hi everybody, welcome to this lecture series on nonlinear systems analysis. We are in week 9 and we have done a lot of things so far now, starting from properties of nonlinear differential equations till bifurcations till stability and so on. So, what I will talk of is one of the concluding lectures of stability analysis before we proceed to other topics. What we have seen so far when we talk of stability is, first we started looking at stability in terms of local linearization, which is also called the Jacobi linearization or the Lyapunov first method or the Lyapunov direct method. There we just look at eigenvalues of the linearized system around a particular equilibrium point, and remember that stability was always defined with respect to a particular equilibrium point. So, I do not have just is a system stable or not was defined with respect to a particular equilibrium, right. For example, the downward position of a pendulum was a stable equilibrium, whereas the upright position was an unstable equilibrium, right. So, we talked about linearization, we talked about defining explicit Lyapunov functions, right. So, and then we had some methods to derive Lyapunov functions, especially the basic ones could be like an energy function or a quadratic Lyapunov function. Then we had the Lassalle's invariance principle, a few converse theorems about Lyapunov stability for nonlinear systems. We also saw extensively of in the previous lectures of this week on explicit Lyapunov based analysis of linear systems and different notions of stability and how exponential stability and asymptotic stability are in a way the same concepts when it is a linear time invariant system, and what exactly a Lyapunov construction of a Lyapunov function means. So, in all this analysis, or even while doing the bifurcation analysis, we were interested, or we kind of postponed some analysis to the later part. Namely, when I was looking at what happens when the linearization has a 0 eigenvalue, right. So, as a parameter varied, we were looking at the change of or a bifurcation was defined when when you cross the imaginary axis as your parameter varies, when the linearized version or the system A matrix A crosses crosses a 0 eigenvalue. Right. So, what to do with those 0 eigenvalues? So, I'll briefly give you an introduction to the analysis which is called the center manifold theory, which will give you a method to analyze stability of a nonlinear system when the linearized version has a 0 eigenvalue. And of course, a lot of this will be used for design purposes too. We will not explicitly look at design. This course is mostly based on analysis, and then the design principles will follow, right. But a lot of systems, before you even do the design, a lot of time is spent in analyzing the systems, right. So, we will briefly do the center manifold theorem. Okay. So, first we did the Jacobi linearization. Right. So, we start with a nonlinear system. Let me take it autonomous, x dot equal to f of x, s usually a state vector in Rn, and around an equilibrium point x dot, I will just use the same x, was a x. This is the linearized version, and then a was computed as the df by dx evaluated as x equal to some equilibrium points. And then the nature of A told me a lot of things about local stability of the nonlinear or of the original nonlinear system. Okay. So, most of it was the local nature of an equilibrium point. It was conclusive, right? We could say if all the eigenvalues of A are on the left half plane, then the nonlinear system is locally stable, right, around that equilibrium point. Even if one eigenvalue of A is on the right half plane, then the nonlinear system is also unstable around that equilibrium point, and we saw a bunch of examples. But we never really discussed of what if the linearization has eigenvalues with 0 real part, which does not really conclude anything about stability, right. So, we will start motivating with the help of an example and then build up slowly to a theory. We will first understand what this means. So, now by now we are we know to analyze systems in terms of vector fields. Okay, so these notes I will post it online. I did not make proper slides thanks to the lockdown which we are facing here at IIT Madras. Well, almost a lockdown. Okay, so I start with an example of this form. X dot is a x cube example in R2, and I just linearize about the origin to get something like this, right. So, x dot equal to 0 and y dot is the negative of y, right. And okay, so it's kind of looks in a nice Jordan form. Okay, so first looking at y, what do I see, right. So, in the y direction, the trajectories are stable and they converge to origin, right. So, y dot equal to minus y will ensure that all as t goes to infinity, y of t goes to 0, right. At least the y axis converges to 0. Okay, but we really cannot conclude anything about the stability of an equilibrium in the x direction, because if I am just here, I really do not know which direction to move. If I am just here, I am just here, x dot equal to 0. There is no direction which I could go, right. Okay, so little observations here which will help us build up towards a theory, right. So, so near the origin in the y direction, the trajectory is a curve whose tangent at the origin is the y axis, like here, right. So, this is how the y axis would behave, right. And similarly, near to the origin, the in the x direction, the trajectory is a curve whose tangent at origin is the x axis, but we cannot put arrows on the curve, as the linearization predicts no flow up to the first order locally about an origin. Exactly, up to the first order, because this is how we do the approximation, right. So, we need to determine how trajectories behave on this curve, right. So, and that is what will be called as the center manifold, and we will use mathematically we will write down these two expressions and check what they actually mean. Okay, so let us start in general with a system of the form x dot is f(x) and say that the linearization of this system x dot equal to ax, again x being an n dimensional state vector. So, around this linearization, let us say that at some equilibrium point x star, okay, for stability, okay. So, if A has at least one eigenvalue greater than 0, then we know that the system is unstable. Okay. Then it does not really matter if there are some of the eigen values lie on the origin, or say if I have a system like this which throws up a linearization this way, I do not really worry about what do I do with these 0 eigenvalues, right, or maybe there is an eigenvalue here, because there is already an unstable eigenvalue here, right. So, this is the sigma and the j omega axis. Okay. So, we will rule out these cases where the system where the linearization throws up a natural instability in terms of an eigenvalue on the right half plane. Okay. So, therefore, now once I rule out that possibility that A should not have an eigenvalue in the right half plane, then the eigenvalues of A can be written as some disjoint union of all the negative eigenvalues and all eigenvalues on the imaginary axis. So, these are the eigenvalues in the open left half plane, and then these are the eigenvalues on the imaginary axis. Okay. So, now say in Rn, let us assume that there are L eigenvalues in the open left half plane, right. Then there will be n minus L eigenvalues which are on the imaginary axis. Okay. Now, what we know that well, we can do some similarity transformation on A of the form T A T inverse, which will split my A matrix exactly in the form which has, I can explicitly write down the eigenvalues on the imaginary axis and another component which has eigenvalues in the open left half plane, right. Means that A naught is n minus L cross n minus L matrix and A minus is a L cross L matrix. Okay. So, in the transform coordinates, I can write as Z is T x minus x star, star being the equilibrium. I can write x dot equal to x dot equal to f x of the form. Okay, let us say I split this into Z1 dot, this is this one here, Z1 dot is A naught Z1 plus F naught Z1 Z2, Z2 dot is A minus Z2 plus F with a minus sign. Again, this is 0 and minus as usual will denote the dynamics corresponding to eigenvalues on the imaginary axis, and this will be eigenvalues on the open left half plane. Okay. So, this will be the first n minus L component, this will be the last L components. Okay. And what are these F0 and F naught? F0 and F naught and F minus are certain smooth appropriately dimensioned vector functions representing the second and other higher order terms. Around the equilibrium. Okay, and also in such a way that f0 of 0 0 equal to 0, f minus equal to 0, then df 0 by dz1 to 0, because like we are computing the gradients also at the origin. Okay, now given this, first is okay. So let's first write down what is the center manifold theorem. So let me call this some equation, say 2. Okay, we start with 2. Around the equilibrium point z equal to 0 of an autonomous system x dot equal to fx in the original coordinates. Then for each k is from 2, I will tell you why this restriction on 2 and 3 comes, that there exists a number delta k greater than 0 and a ck mapping phi which goes from z1 such that the norm of z1 is less than this number delta k to RL with phi 0 equal to 0, phi dash the first derivative is equal to 0, such that the surface which is called as the center manifold Z2 is phi of Z1. So, I am writing all Z1 Z2 in terms of Z1 for all Z1 less than delta k, right, and this is such that this is invariant under the dynamics two. Okay. So, therefore, on this center manifold my dynamics would just now look something like this, that Z1 dot is A naught Z1 plus F0 Z1 phi of Z1. Okay. Now, what is a theorem that then will tell us about stability? Okay. So, if this, which I call this 3, Okay, so we say let 3 represent the dynamics on a center manifold how is the center manifold given? This is Z2 is phi of Z1, then Z1 equal to 0 is locally asymptotically stable or just stable or unstable for 3 implies that Z1 Z2 equal to 0, the equilibrium of the original system is the same, locally asymptotically stable, locally stable or unstable, right, for 2. Okay. So, I am just looking now at the stability of this equation, right, and if this is stable, then the original system in this the original transform system in this coordinates is also stable, asymptotically stable or unstable. Whatever is the property of this system will be translated to the property of the system. Okay. Now, first is so what do I do with this result and how do I actually conclude whether a given system is stable or not. So, first what we have to look at is okay. So, I am essentially looking at this dynamics, right. So, let us write down this here. Z2 is phi of Z1. Okay, let me differentiate this. So, I have Z2 dot is, how do you say, phi dash of Z1 dot. Okay, so what is my my Z2 dot? If I just substitute here, I have A minus with Z2 plus F minus Z1 Z2 is d phi by d Z1 times Z1 dot. What is Z1 dot? This is A naught Z1 plus F naught Z1 Z2, okay, like this, right. So to arrive at system 3, right. So why do I want to do this? Because if I just evaluate stability of the system 3, then it will tell me stability or otherwise of the system 3, it will tell me the properties of the original system, which is given by the system with equation 2. Okay. Right. So again, so this will again together be with conditions of phi 0 is 0, phi dash 0 is also equal to 0. Okay. And then the reason we want this function to be of for each k is, okay, we are excluding like all these linear functions, right. So which where Z1 and Z2 could be like linearly related. We will see that also when we do an example. Okay. So first is now how to find phi. Right. So if I label this as equation 4. So, this phi is a solution to the partial differential equation 4. Okay, I just have an equation here. So, I know what is a minus a naught. I possibly know these functions. So, I just could solve a PDE, which may sometimes be analytically difficult to solve PDE. So, can we just look at some approximate methods which can give us some phi which is close to the solution or also equal to the solution, right? Okay, so can we find an approximate solution? Okay, so let us just set another theorem and we will learn how to use this. Okay, I'm skipping the proofs, but we'll just, as I said, we'll just learn how to learn this process. So, okay, suppose I have instead of phi some phi tilde which goes from Rn minus L to RL, right? And it's a C2 mapping. Okay, so which satisfies phi not equal to phi at 0 equal to 0, phi dash at 0 also equal to 0. Right, and for some q greater than 1, suppose that this phi tilde of z times plus z1 comma this. I am writing everything in the new in the approximated phi denoted by phi tilde. Minus a minus phi tilde z1 this is of some order of z1 to the power q for z1 tending to 0, then the approximated phi tilde and the original phi tilde, original phi are related this way. Okay. The order of this one for z1 going to 0. Okay, so this is okay. So what we are trying to do is trying to find a way to approximate the phi, which may sometimes be analytically difficult to compute. Okay, so I just quickly do with the help of an example, and then we'll post a couple of examples online, so that that will help you practice a little more problems. So start with a simple system, which again in R2 I have x1, x2 plus x1 cube plus x1 x2 square. I have minus x2 here, minus twice x1 square plus x1 square x2. Okay. So, I am just looking at linearization around 0 comma 0, and then you see that it has a 0 eigenvalue, and I am looking for the center manifold of the form phi 2 is phi of x 1. Okay. Again with phi 0 is 0, phi dash of 0 also equal to 0. Okay. So, let me just say that phi tilde as a function of x 1 is a C2 function, twice differentiable function. Phi tilde 2, let me call this coefficient as phi tilde 2 x 1 square sum phi 3 tilde x 1 cube and so on. So, what I do is now take this phi, okay, and then write down with this phi tilde, okay, this is my approximate phi tilde, and write an equation like this. Okay. So, should be simple, right. So, so I will have phi tilde. So, this expression on the right hand side. So, I will write, okay, let us write the expression on the left first. This is phi 2 tilde plus 2 x 1 square plus phi 3 tilde x 1 cube plus some other terms of order 4. Okay. So, what I am doing is I am just taking this phi tilde of x 1 and just substituting it here, right, and what are the exact dynamics here? Those are given by this x 2 terms here, right. I am just substituting this phi, approximate phi over here. Okay. What does this equate to? This equates to this expression on the right here, right. So, that will look something like phi tilde dash x 1 times x 1, right. I have substituted here x 1, then x 2 is phi of x 1. What is phi of x 1? I just write down this approximation here, phi tilde x 1 plus I have x 1 cube plus x 1 phi tilde square of x 1 plus okay. So, just so very simple thing of substituting this into this one, or into this equation number 4. Okay. It's a little okay, lengthy process, but it's purely mechanical. So, if you do once we do all the manipulations, what we find is the following, that phi of x 1 is simply minus 2 x 1 square plus O of x 1 cube. Okay. Now, if I substitute this into the dynamics, of the center manifold, okay. So, what do I get? I get is x 1 dot from this expression. So, d by dt of x 1 is x 1 times x 2 plus x 1 cube plus x 1 x 2 square, right. Okay, so what is x2 is phi of x1 from here. So, this phi of x1 with x2, so I will have x1, x2 is phi of x1, that will be minus 2 x1 square plus x1 cube plus other terms of order 4. So, that will give me minus x1 cube plus other terms of order 4 and above. Okay. Now, for this, right, x1 equal to 0 is, because of this minus x1 cube, is a locally asymptotically stable equilibrium point. And therefore, for the original system, 0 0 is also a locally asymptotically stable equilibrium point. Okay, so this is a little illustration of how to analyze systems for which the linearization throws up a 0 eigenvalue or eigenvalues on the imaginary axis via the center manifold theory. We will not really go deep into the details of what if the systems are of order 4 and higher, but just to give you a little glimpse of how will you handle systems for which there are eigenvalues on the imaginary axis on during the Jacobi linearization, right. So, we will put up some problems for you to solve, they might be helpful for you to answer more or solve more problems or questions by yourself, and also help you answer the assignment problems. So, you can always post questions online if you have. So, this was about the theory on center manifold, a very brief introduction. Thanks for listening.